Okay, so we're going to find the eigenvalues for this matrix. I'm double checking for -1, 0, 0, 0, 2, -1, 4, 3. This matches the question. I pulled this number 14 out of the book. So we're going to go ahead and find this one. So this will have up to 3 lambdas because it's a 3 by 3. And I am going to go ahead and write out with the a minus lambda I. So that means this is going to be 4 minus lambda. This is going to be negative lambda, and this is going to be 3 minus lambda, and this is -1, 4, 0, 2, -1, 0. So we need to find the determinant of this and set that equal to 0. So I'm just, when you do these, the biggest thing is, how can I do this to make this the simplest way possible? So I am just going to take a look at this and decide, what will make my life the easiest in terms of finding the determinant. And so I'm just going to go across the top row just because there's no double zeros anywhere. So I'm going to go ahead and do 4 minus lambda times, and this is negative lambda 2 for 3 minus lambda. And then minus 0 times, and that doesn't matter because it's 0. And then minus 1, because it's a -1, times -1, negative lambda, 0, and 2. And so then I'm going to double check just because I can go kind of cross-eyed. So I did this row, column, and this row, and then I'm left with this, so that works. And then I did the 0, and it doesn't matter because that whole thing will cancel out. And then the -1, and I'm left with that block. So we're good, at least in the writing out. So now I'm going to go ahead and solve the next line, which is to say that this is 4 minus lambda. And then this is going to be negative lambda times 3 minus lambda minus 8 minus 1 times -2, and then there's the 0. And so this is going to be 4 minus lambda times -3 lambda plus lambda squared minus 8 plus 2. And distributing, that is -12 lambda plus 4 lambda squared minus 32 plus 3 lambda squared minus lambda cubed plus 8 lambda plus 2. So I'm going to put this in right order. Remember, this is all equal to 0. So this is negative lambda cubed. Done with that one. Then I've got 4 and 3, so plus 7 lambda squared. And then -12 plus 8 is -4 lambda. And then -32 plus 2 is -30 equals 0. I'm going to divide out that -1 just because that's going to be even harder to factor than it already is. So, and when I divide it out, it's just going to go back to where it was because it's 0. So now I've got that relationship, so we're good. So now I need to think about what could go in here. Now it's a cubic, so we have to go ahead and think about a root. So that could be 30 and 1. It could be 6 and 5. It could be 10 and 3. It could be 15 and 2. It could be any of those. We just need to figure out one, and if we can figure out one, we can divide it out and get the rest. So I'm going to pause this here because you don't need to see me work through all this division, and we're just going to work till we find a root. Okay, so after some work, I was able to determine that one of the eigenvalues is 5 in the order of x minus 5. So if you divide out x minus 5, you're going to get lambda. I shouldn't say x, I should say lambda. Lambda minus 5, and then it's lambda squared minus 2 lambda minus 6 equals 0. And that's a quick check to make sure you're right. Lambda cubed minus 2 lambda squared minus 6 lambda minus 5 lambda squared and plus 10 lambda and then minus 30 plus 30. So, and then if you combine those, you get the negative 7 lambda there, and you get positive 4 lambda there. So this is a match. The problem is this piece, because that's non-factorable. So I kind of like this problem because even though it's a little bit more challenging than what I put on a test, it kind of exposes all the things. I mean, you go about solving the characteristic equation in that manner, and then you create the characteristic polynomial. And I'm left with lambda minus 5 times this lambda squared minus 2 lambda minus 6. So one eigenvalue is definitely lambda equals 5. But now I'm wondering about this one. So I'm going to go ahead and plug this into the quadratic since it doesn't appear to factor. So let's go ahead and call that 2 plus or minus the square root of 4 minus 4 times 1 times negative 6. So this is good. We're not going to end up with anything imaginary, although complex lambda values are a thing, times 2. So this is going to be 4 plus 24. So this is 2 plus or minus over 2 square root of 28, right? And 28 is 14 times 2, and that's 7 times 2, so 4 is in there. So that would be 2 rad 7. So this is the same as 2 plus or minus 2 rad 7 over 2, divide out the 2's, so that's 1 plus or minus rad 7. So here are 2 eigenvalues, and here is my third eigenvalue. So I have 3 real eigenvalues. One of them is irrational. So lambda 5, lambda equals 1 minus rad 7, lambda equals 1 plus rad 7. So now that we have that, we would have some calculator work to do to find the eigenvalues. So going back to the A, I'm going to go ahead and lasso this so I can use it again. Down there. Oops. All right. So now, let's go ahead and put in one of the irrational ones first. So I'm going to do 4 minus 1 rad minus 1 rad 7. Ooh, let's do the plus 1. Let's do that one first. Let's work our way backwards. So 4 minus 1 plus rad 7, negative 1 minus rad 7, 3 minus 1 plus rad 7, and then it's going to be negative 1, 0, 0, 2, negative 1, 4. And remember, we're setting this up against 0, 0, 0 to determine a solution to a homogeneous system. So I am going to go ahead and plug this into my calculator. So I ended up with irrational. I have x1 equals 2.823 x3. X2 equals negative 0.323, excuse me, positive x2, x3, and x3 is free. So if we plug these in exactly, so this comes out to be x3 times 2.823 and 0.323 and 1. We're going to get close but not exact. So I'm going to go ahead and plug this in and put it against A to see what I get. Okay, so to check my work, I went ahead and went off screen for a second, and I did A. So let me get my little lasso-y thingy again. I did A right there. And then I took A and I took my my eigenvector there, 8, 2, 3. So I got this going too. So I got that drawn in. And I multiplied those together. And I ended up with this nasty thing, 10.292, 1.77, and 3.646. So that's what I get when I multiply a and x together. So then the next question is lambda and x, which would be, in this case, 1 plus root 7 times 2.823, 0.323, and 1. And I got 10.292 and 1.717. Oh, and that was true. I got that too. 1.177. And then I got 3.646. So this and this, or ax and lambda x, match. So I feel pretty confident about my eigenvalue and my eigenvector at this point. So you could repeat this process with 5 and 1 minus rad 7. Like I said, this is about as challenging as they get, but in terms of solving the 3 by 3 determinant, this is the process, whether you get 3 real or 3 non-real or whatever. And then I like that this demonstrated something other than a whole number. You can get irrationals, you can get fractions, you can get anything under the sun. And like I said, if you look ahead past what we're going to be doing in this unit, you can get complex eigenvalues. And so eigenvalues exist on the complex plane, just like roots exist on the complex plane. So basically anything that could be a root could also be an eigenvalue. And that includes rational numbers and irrational numbers and imaginary numbers. Okay? So at this point, I'm only going to do these 3 videos. There's also readings that you can do and examples in the book that you can view. And I'll see if I can't find some additional videos online if you're really struggling with this whole eigenvalue process to help you get through it.